Hi, I'm Mark Barsamian. In this video, we'll be discussing the end behavior of polynomial functions.
Remember that a polynomial function is a function such as maybe this one, or maybe this one. So a polynomial consists of a sum of one or more expressions of the form cx raised to the p, where c is a real number constant called a coefficient, and p is a non-negative integer power. That is, p is an integer and p is greater than or equal to 0. The terms of a polynomial are expressions of the form cx to the p. That is, a term of a polynomial consists of a power function with a non-negative integer power multiplied by a real number coefficient. Consider some special cases of polynomial functions. Functions such as f of x equals minus 3x plus 5. Notice that in equation form, this would be y equals negative 3x plus 5. In other words, an equation for a line. Another kind of polynomial function is a function like this. This is a constant function. In equation form, this would be y equals 5, an equation for a horizontal line. So this qualifies as a polynomial because it can be rewritten as f of x equals 5, which is equal to 5 times the number 1, which is equal to 5 times x to the 0 power. So in other words, a power function with a non-negative integer exponent multiplied by a real number. So that is a polynomial. It's what's called a constant polynomial. And another kind of polynomial, a special kind of polynomial, is this one, f of x equals 0. This is a particular kind of constant function. In equation form, this would be y equals 0. So we're an equation for a horizontal line. This qualifies as a polynomial because it could be rewritten in the following way. F of x equals 0, which could be written as 0 times 1, which could be written as 0 times x to the 0 power. So in other words, a non-negative integer power of x multiplied by a real number constant. So this is a polynomial. It's called the zero polynomial, and it's a special kind of constant polynomial. So those are three particularly simple-looking cases of polynomial functions. The fact that the zero polynomial, f of x equals 0, qualifies to be called a polynomial is a bit of a nuisance. It makes definitions of some of the terminology associated with polynomials a little bit more complicated. But we can define these terms, the leading term, the degree, and the leading coefficient, and the constant term. We can only define these for non-zero polynomials. They're not defined for the zero polynomial. All right, well, the leading term of a polynomial is the non-zero term that has the highest power. The degree of a polynomial, the degree of a non-zero polynomial, is the power that appears in its leading term. The leading coefficient of a non-zero polynomial is the coefficient of its leading term. And finally, the constant term of a non-zero polynomial is the term of the form plus c, where c is a real number constant. Now, the constant term cannot be 0. These definitions can be better understood if we consider some examples. So in example 1, for this polynomial function f of x, the leading term is 6x to the 5th. The degree is 5. The leading coefficient is 6. The constant term is negative 13. So this came from there. The 5 came from just the exponent. The 6 came from the number out front, and the number negative 13 came from out here. The constant term is the number with its sign. Now, for this function, the leading term is negative 4x to the 8. The degree is 8, and the leading coefficient is negative 4. The constant term is 0. So notice that the leading term does not have to be the term listed in front presentation of the function. It's the term that has the highest power. And also notice that the constant term can be the number 0. That is, if there is no constant sitting out here, that's the same as saying plus 0. So the constant term can be the number 0. For the function f of x equals minus 3x plus 5, the leading term is minus 3x. The degree is 1 because x can be written as x to the first power. The leading coefficient is minus 3. The constant term is the number 5. For the next example, we're going to consider the function f of x equals 5. This is a constant function. For this function, the leading term is 5. Its degree is, well, we have to think about what's the power of x appearing in the leading term. We can think about rewriting the 5. So we can rewrite the function, or we can think of the function as 5 times x to the 0 power. So in that presentation, it's very clear that the power in the leading term is the number 0. So the degree is 0. The leading coefficient is the number 5, because that's the number that's sitting in front of the power function in the leading term. The constant term is the number 5. So this is a polynomial where the leading term is the same as the constant term. There's only one term in this polynomial, and it gets to play the role of both the leading term and the constant term. Now consider the function f of x equals 0. This is a constant function, and it's the 0 polynomial. So all of these things are not defined. So notice that we don't have any of these terms defined for the 0 polynomial. We do have them for a constant polynomial. So we can have a degree that's the number 0. That happened here. But we cannot find the degree of the 0 function, the 0 polynomial. So the 0 polynomial does not have degree 0. The degree is not even defined for the 0 polynomial. A constant function does have a degree that's 0. So it's an important distinction. A couple of observations. The leading term is not necessarily the one that appears in the left end of the presentation of the function. We saw this happen in example 2 above. Remember that addition is commutative, so the terms of a polynomial can be relisted in any order as long as the correct signs get attached to the coefficients without changing the function. So this function f of x that's written with the leading term second in the list could be rewritten this way. So there are a bunch of different ways we can reorder the terms of that polynomial, and it doesn't change the function at all. So in all three of these presentations, the leading term is negative 4x to the 8. And again, the degree can be 0, as we saw in example 4. Now, the constant term can be the number 0. That's what we saw in example 2 above. Again, this function has a constant term that's the number 0. But the leading coefficient cannot be 0. That is, the function from example 2, for instance, could be rewritten in the following way. I could rewrite it that way, but that does not change its named parts as a polynomial. That is, its leading term is still minus 4x to the 8th. Its degree is still 8. Its leading coefficient is still minus 4. And its constant term is still 0. So that's the end of our review of polynomial functions. Now let's get on with the main topic of this video, the end behavior of polynomial functions. Remember that the phrase end behavior refers to the left end or right end of a graph. We'll be interested in describing the end behavior in words and also describing in more abbreviated notation. Now, since describing the behavior of the end of a graph involves describing a trend, it's natural to describe the end behavior using the terminology of limits, because remember that limits describe trends. So, for example, the right end of a graph is the portion of the graph where the trend in the x values is the following. X gets more and more positive without bound. Abbreviating that in words, we would say x goes to infinity. Abbreviating in symbols, we would write, we will be interested in the behavior of the graph at the ends. That is, does the end of the graph go up or down, or does it level off? In other words, we'll be interested in identifying the trend in the y values. More precisely, for the right end of the graph, we'll be interested in identifying the following. We'll be interested in identifying the limit as x goes to infinity of f of x. In symbols, we would abbreviate this. So let's discuss the end behavior of constant polynomials. The simplest kinds of polynomials, the constant polynomials have end behavior that's trivial to describe. For a function like this, you could describe the end behavior as this. The y value is constant at the end of the graph at height y equals c. So the corresponding limit description would be the following. The limit as x goes to infinity of f of x is the number c. That is, the trend in the y values is that the y values are getting closer and closer to c. Well, they're actually equal to c, and so we write this limit symbol to denote that. What about the end behavior of non-constant polynomials? Well, for non-constant polynomials, the ends of the graph always go up or down, depending on the degree of the polynomial and the sign of the leading coefficient. And the behavior could be summarized in this table. So for instance, for an odd degree polynomial with a negative leading coefficient, the graph goes up on the left and goes down on the right. And that would be summarized in or abbreviated in limit symbols as saying this symbol, or writing this symbol for the fact that the graph goes up on the left, and writing this symbol for the fact that the graph goes down on the right. Let's return to our earlier examples and describe the end behavior in words and limit notation. For example 1, for the function f of x equals 6x to the 5th minus 4x cubed plus 11x minus 13, notice that it's an odd degree polynomial with positive leading coefficient. So the degree is 5, so it's an odd degree, and the leading coefficient is the number 6, so it's positive. So the end behavior is, well, let's go up and look. Odd degree polynomial with positive leading coefficient. So here is a summary of the end behavior. The graph goes down on the left and goes up on the right. If we abbreviate this in limit notation, it would look like this. So the graph goes down on the left is abbreviated with this symbol, and the graph goes up on the right is abbreviated with this symbol. Okay, let's do another one. For this function, f of x equals 6x to the 5th minus 4x to the 8th plus 11x, this is an even degree polynomial with negative leading coefficient. So what's the end behavior? Well, let's go up to our table and see. Even degree polynomial, negative leading coefficient. An even degree polynomial with negative leading coefficient goes down on both sides and has limit behavior described by these symbols. So the limit as x goes to negative infinity of f of x is negative infinity. That is, the left end of the graph goes down. And the limit as x goes to plus infinity of f of x is also negative infinity. That is, the right end of the graph also goes down. Consider the function f of x equals minus 3x plus 5. This is an odd degree polynomial with a negative leading coefficient. The coefficient is easy to see. It's this number negative 3. For the odd degree, it's important to remember that the variable x can be rewritten as x to the 1. That's where we get the odd degree. So what's the end behavior of an odd degree polynomial with a negative leading coefficient? Well, the graph goes up on the left end and goes down on the right end. So the end behavior described in limit notation is so the fact that the left end of the graph goes up is abbreviated with this symbol, and the fact that the right end of the graph goes down is abbreviated with this symbol. Now, for the function f of x equals 5, this is a degree 0 polynomial. That is a constant function. Remember that our table only applies to non-constant polynomials, non-constant polynomial graphs. So we just know by looking at this function what the end behavior is. The left end of the graph is constant at height y equals 5, and the right end of the graph is constant at height y equals 5. So that described in limit notation would be the following. The limit as x goes to negative infinity of 5 is 5, and the limit as x goes to plus infinity of 5 is also 5. Finally, for the function f of x equals 0, this is also a constant polynomial. So the end behavior is that both ends of the graph have constant height, y equals 0. And in limit notation, we would write the limit as x goes to negative infinity of 0 is 0, and the limit as x goes to infinity of 0 is 0. That's the end of the video. Thank you.